The Krug was a Soviet surface-to-air missile system designed to engage fast-moving targets. In the late 1950s, the Soviet military faced a significant tactical challenge. Western jets were flying at speeds and altitudes that rendered traditional anti-aircraft artillery ineffective. Anti-aircraft fire could not reach those altitudes in time. Tactical aircraft were operating at over 500 knots. Air power was expected to play a decisive role in potential conflicts. The Soviet Union required a new solution. Without it, their tank and motorized rifle divisions would be vulnerable to aerial bombardment. At the time, existing Soviet surface-to-air missile systems were designed for strategic territorial defense, rather than protecting mobile forces. In 1955, the S-25 Berkut entered service, built specifically to defend Moscow. This system was stationary, relying on large radar arrays and permanent concrete emplacements. The Berkut was fixed in place around the capital. 2 years later, the S-75 system was introduced. While it could be relocated, it was not highly mobile. It required hours to dismantle the radar sites, transport the equipment, and set it up again. In a combined arms offensive operation, a tank division might break through opposing lines. They would be followed by motorized rifle troops in armored personnel carriers and infantry fighting vehicles. These armored formations could advance dozens of miles a day. However, this rapid movement created vulnerabilities to airstrikes. By the time an S-75 system could be deployed, frontline troops would be out of range. This left them exposed to aircraft. Consequently, the SAM systems of that era were ineffective in a mobile tactical role. They could not effectively cover an advancing army. The Soviet military leadership recognized this limitation. In 1958, they issued new requirements to their engineers. The goal was to develop a surface-to-air missile system capable of reaching targets at the same altitudes and ranges as strategic SAMs. Crucially, this system had to keep pace with mobile armored units. It needed to deploy and relocate in a matter of minutes. The engineers were tasked with integrating the capabilities of a stationary defense site into a mobile self-propelled unit. The Scientific Research Electromechanical Institute took on the development. Veniamin Efremov was appointed as the chief designer. He had prior experience in designing air defense systems. His team faced numerous complex technical challenges. The new system was named Krug. The first major challenge was the chassis. Previously, air defense systems were mounted on trailers or wheeled trucks. These wheeled vehicles struggled in rough terrain. They could not keep pace with tracked armored columns. Efremov determined that a different approach was necessary. He collaborated with heavy machinery designers in Kharkiv. They were tasked with designing a purpose-built tracked chassis capable of carrying heavy equipment across rough terrain. The Kharkiv team met these requirements. They developed a vehicle capable of reaching 40 miles per hour and navigating the same obstacles as main battle tanks. The second issue was self-sufficiency. In combat, there is no time to look for an external power source to run the radars and fire control computers. Because of this, every vehicle in the system was fitted with its own auxiliary power unit. This allowed them to operate independently. Designers also equipped the vehicles with full NBC protection, safeguarding against nuclear, biological, and chemical threats. Crews could operate from fully sealed cabins. This made it possible to function even in irradiated zones. Development took 6 years, involving extensive testing and modifications. The engineers addressed unique technical challenges, as nothing like this existed at the time. In 1965, the Krug system officially entered service with the Soviet military. The maximum engagement range was roughly 45 kilometers, or about 28 miles. This meant an inbound aircraft would be tracked by radar early on. This reduced the time available to drop its ordnance. The maximum engagement altitude reached 77,000 feet. That covered the flight envelope of most aircraft of that era. It put both tactical and strategic bombers in the engagement zone. The system's missiles could intercept targets flying at speeds up to Mach 2.4. The core of the system was the 3M8 surface-to-air missile. It incorporated the advanced technology of its time. The missile was 28 feet long and weighed 5,500 pounds. That is roughly the weight of a full-size pickup truck. To launch the missile and accelerate it to intercept speed, 4 solid rocket boosters were attached to the sides of its body. At launch, these generated enough thrust to propel the missile off the rail. They also provided acceleration during the initial flight phase. Within a few seconds, the solid fuel was entirely spent. The boosters were then automatically jettisoned. By that point, the missile had built up enough speed. This allowed a ramjet sustainer motor, running on standard jet fuel, to activate. The mechanism was straightforward. Incoming high-speed air entered the intake, where it mixed with atomized fuel and ignited. The exhaust gases exited the nozzle, generating thrust. The faster the missile flew, the more air entered the engine. This produced even more thrust. This setup allowed the missile to sustain supersonic speeds all the way to the target. The missile relied on radio command guidance sent from the ground station. Dedicated tracking radars monitored the positions of both the target and the missile. They calculated the necessary course corrections. The system then transmitted those updates to the missile via a radio data link. Once the gap shrank to 50 meters, a radar proximity fuse triggered, detonating the warhead. The single-shot kill probability stood at roughly 75%. This was a metric verified during live-fire exercises. The primary tactical unit of the Krug system was the SAM battalion. At its core was the Target Acquisition Radar. This was a 360-degree search radar mounted on a tracked chassis. The antenna rotated continuously, scanning the surrounding airspace. The system could track incoming aircraft from tens of kilometers away. Beyond detecting them, the radar also interrogated the contacts. It used an IFF, or Identify Friend or Foe, system. Combat operations were handled by 3 SAM batteries. These reported to the battalion commander. Each battery featured an engagement radar and 3 self-propelled transporter erector launchers, known as TELs. The engagement radar utilized a smaller antenna. It provided tracking on a selected target and guided the interceptors. The TELs were tracked vehicles equipped with twin launch rails. Each battery had 6 missiles ready. This allowed the entire battalion to keep 18 interceptors ready to fire. The battalion's technical support battery maintained the unit's combat readiness. It included truck-mounted maintenance and repair stations. These were capable of fixing malfunctions in the field. Transporter loader vehicles brought up fresh missiles to reload the TELs. Dedicated fuel trucks kept the vehicles fueled. This allowed the battalion to operate autonomously. They were independent of fixed supply bases. The system could displace, keep pace with advancing armored columns, and deploy at a new location in a matter of minutes. During operations, the Krug system functioned through coordinated steps. This began with the battalion moving to a designated area. The tracked vehicles advanced in a column. They crossed rough terrain and shallow water hazards. The system was designed to keep pace with the armored units it protected. Upon arrival, the battalion deployed into firing positions directly from the march. They did this without the need for extensive site preparation. The target acquisition radar was set up in the center of the combat formation. Meanwhile, the launchers took up pre-calculated positions around it. Deployment took approximately 5 minutes. This was a significant improvement over older systems that required hours for similar procedures. Displacing took a similar amount of time. This increased survivability on the battlefield. The deployment process was highly automated. Crews could perform necessary operations from inside their armored compartments. Onboard systems handled positioning by plotting the coordinates of each vehicle. Then all elements of the battery aligned and networked with each other. The radars and launchers functioned as a single unit. Combat control signals were transmitted between vehicles via secure radio links. This eliminated the need for communication wires. The battalion command post was located inside the cabin of the target acquisition radar. A circular radar scope displayed airborne targets within range. The rotating roof antenna swept the sky to detect approaching aircraft. Upon target detection, the system automatically sent an IFF interrogation. If the target did not reply with the correct codes, it was classified as hostile. The battalion commander would assess the air picture. Then he would make the call to engage. After picking out the highest priority target, a single push of a button sent the targeting data to one of the 3 batteries. Inside the chosen battery engagement radar, an indicator would instantly light up. This alerted the battery commander to their new target. At that exact moment, the radar antenna automatically slewed toward the incoming aircraft. From there, it locked on and began tracking. The main difference between the engagement radar and the search radar came down to one thing. It did not sweep the entire sky. Instead, it focused a tight pencil beam directly into a specific sector to paint the target. This provided highly precise tracking data. The battery commander could see the target blip on his scope. He monitored the engagement and waited for the optimal moment to give the launch command. Meanwhile, the system automatically assigned a specific launcher. It also selected the optimal missile for the shot. Each mobile launcher carried 2 missiles. The fire control system calculated which one had the best firing solution. The launcher traversed to face the target. Then the missile received its final pre-launch data updates. The target entered the engagement envelope. Then the battery commander initiated the launch. The solid rocket boosters ignited. The missile left the rails, racing toward the target. The engagement radar simultaneously tracked both the missile and the target aircraft. The onboard systems of the missile picked up the radio guidance commands and adjusted its course. The distance to the target closed rapidly. This entire process, from detection to launch, took less than a minute. In those 60 seconds, the targeted pilot had limited time to change course or employ electronic countermeasures. Escaping the engagement zone was difficult. An aircraft tracked by the Krug system faced a high probability of interception. On the radar scopes, the intercept unfolded as 2 glowing blips moved toward each other until they merged into one. At that exact moment, the proximity fuse detonated. A cloud of fragmentation from the warhead was designed to damage or destroy the target aircraft. The battery commander confirmed the intercept and reported back to the command post. If the first missile missed, a follow-up shot could be fired immediately. Live fire exercises on the test ranges demonstrated the capabilities of the Krug system. Target drones simulated modern combat aircraft and were frequently intercepted. The air defense crews drilled to improve their reaction times. With this system, the Soviet Army gained a capable defense against tactical airstrikes. The introduction of the Krug system prompted Western military analysts to reassess their strategies. They realized that standard high-altitude bomber tactics were becoming less effective. For decades, altitude was considered a combat aircraft's best defense. The higher a bomber flew, the harder it was to hit with anti-aircraft fire. Plus, the crew had more time to spot a threat and take evasive action. This tactic had been standard since World War II. However, the development of new surface-to-air missiles forced a shift in existing concepts of air combat. The Krug system could engage targets at altitudes approaching 75,000 feet. That was a ceiling out of reach for many tactical aircraft. Strategic bombers could fly even higher. But up there, longer-range SAM systems were waiting for them. This layered air defense network significantly increased the risks for aircraft operating within that airspace. Western tacticians searched for a workaround. The solution was to fly at extremely low altitudes. At lower altitudes, radar performance degrades significantly. Systems suffer from ground clutter bouncing off trees, buildings, and the terrain itself. An aircraft flying 100 feet off the ground blends into the background clutter. This makes it highly difficult for radar to detect. The window to detect and engage such targets shrinks drastically. They appear over the radar horizon at the last moment. American aerospace designers began working on a new generation of strike aircraft. These were purpose-built to operate at extremely low levels. A key example of this concept was the F-111 tactical bomber. First flying in 1964, the aircraft introduced advanced technology. Its variable sweep wing allowed it to fly efficiently at supersonic speeds while operating at low altitudes. In automated terrain, following radar handled the low-level flight. The F-111 could maintain an altitude of less than 300 feet, following the contours of the landscape. Opposing radars struggled to track it due to the massive amounts of ground clutter. This method of penetrating air defenses became known as terrain-following flight. It became standard for Western strike aircraft. The Soviet military monitored these developments and initiated an upgrade of the Krug surface-to-air missile system. Originally, the system could not engage targets below 10,000 feet. A shift toward low-level flying was not initially anticipated. This 10,000-foot lower limit created a gap in the air defense network. Designers at the Scientific Research Electromechanical Institute were tasked with modifying the system. Engineers had to upgrade both the engagement radars and the missiles. The main challenge occurred at low altitudes. This is where radar beams bounce off the Earth's surface. This causes multipath interference and false returns. It makes it difficult to maintain a radar lock on the target. Engineers developed new algorithms to process the radar data and filter out the ground clutter. The upgraded system was designated Krug A. The minimum engagement altitude was reduced to about 800 feet. This allowed it to intercept low-flying aircraft. The subsequent variant, Krug M, lowered this limit to under 500 feet. This required opposing aircraft to fly at extremely low altitudes to stay below the SAM's engagement envelope. The upgrade improved other aspects of the system as well. The radar equipment became more resistant to jamming. This allowed it to operate in electronic warfare environments. System reliability increased, and maintenance times were reduced. The missiles were fitted with improved proximity fuses to increase the probability of target destruction. The cat-and-mouse game between strike aircraft and air defenses entered a new phase during the Cold War. Every time one side made an improvement, the other side countered it. Airplanes were becoming more advanced. They were flying lower and faster. In response, surface-to-air missile systems expanded their engagement envelopes. This reduced safe corridors for penetration. This arms race continued for decades. The Krug system remained a notable component of Soviet military technology. The Krug had a specific role in the Soviet Union's air defense network. Other surface-to-air systems protected cities, factories, and strategic sites. Meanwhile, the Krug was built as a tactical defense system for the Army. It sat at the top of the tactical air defense hierarchy. It was deployed to defend major frontline military formations. Army and front headquarters, communication hubs, and fuel and ammunition dumps were covered by its range. Field hospitals and repair bases were also guarded by these SAMs. Krug missile battalions were part of larger surface-to-air missile brigades. These were attached directly to combined arms and tank armies. This structure gave commanders the flexibility to shift firepower. They could concentrate systems along high-threat sectors. Brigade commanders received the broader air picture from higher headquarters. They had the autonomy to engage incoming strikes. This setup allowed them to react to incoming threats. Serving in these SAM units required technical proficiency. Both soldiers and officers went through extensive training. They had to operate complex hardware. They also ran regular drills to function as a crew. Live fire exercises on the test ranges maintained their operational readiness. These missile crews were responsible for the air defense of large ground troop formations. Operating the Krug demonstrated its capabilities across different environments. The hardware was deployed in various climates. This ranged from the Arctic to Central Asian deserts. The Kharkiv-built tracked chassis provided cross-country mobility. The electronics were designed to function in both sub-zero temperatures and high heat. Beyond the Soviet Union, The Krug saw service with Warsaw Pact nations. They received these systems for their air defense networks. Czechoslovakia, Hungary, and Poland deployed Krug battalions. Soviet personnel provided training on the hardware, combat tactics, and maintenance. Air defense crews from these countries trained at Soviet military academies. They also took specialized courses to operate the systems. The crews also trained on firing ranges. Joint Warsaw Pact military exercises regularly featured scenarios with these SAM units. Krug battalions from different countries operated together. They practiced the coordination of air defenses to intercept simulated strikes. As military technology progressed, combat aviation evolved. New types of aircraft and cruise missiles entered the battle space. Electronic warfare capabilities advanced. This increased the demands on air defenses. Designers developed next-generation systems. The Krug eventually reached the limits of its upgrade potential. In the early 1980s, the S-300V surface-to-air missile system began replacing the aging Krug. This new system incorporated 2 decades of technological advancements. It outperformed the Krug. It featured a greater effective range and better resistance to electronic countermeasures. The system could also engage multiple targets simultaneously. Crucially, the S-300V could intercept not just aircraft, but tactical ballistic missiles as well. This was an important development given the rapid proliferation of missile technology. Krug battalions were gradually phased out of the Soviet Army. They made way for more modern systems. However, in several nations, the Krug remained in active service for years to come. It continued to provide airspace defense for ground forces. The Krug system represents a notable chapter in the history of Soviet weaponry. Its development demonstrated the capacity of engineers to address complex technical challenges and produce functional military hardware. Veniamin Yefremov and his team delivered a reliable weapon system. It served as the primary air defense for Soviet ground forces for 2 decades. The design principles and technical solutions they pioneered laid the groundwork for future developments. This formed the baseline for subsequent mobile SAM systems. If you enjoyed this video, be sure to drop a like. Let me know in the comments what other military hardware you would like to see covered next. Make sure to subscribe to the channel so you do not miss out on any new episodes. These episodes explore the history and design of various weapon systems.